The title of my talk is History, Future, Present, and I need to sort of qualify that. I call it future present because I don't know exactly where future falls. It's already here, and you in the sort of same space and time. It's not something that we can talk about as if it's going to happen 50 years from today. It's going to have to happen now. The history part that I need to explain is it's a non-linear history that I'm interested in. There is one slide which will give you chronological order in which steel as a major construction material was applied over the globe. I'm preaching the choir. Everybody knows the qualities and benefits of steel and how it's actually of great sort of number of properties that make it very desirable, etc., etc. So I don't want to sort of go through the list. You can read it for yourself. The photograph is very interesting because that's the photograph of steel construction that sort of took off in the U.S. It's kind of symbolic photograph. It's not the first building that was made using steel frame. Empire State Building and the sort of the euphoria about this newfound material and its use. So the non-linear part of history that I'm going to speak about is how has it become a go-to material for architects and designers. It's always been used for major infrastructure projects across the globe. It's been used in large footprint buildings across the globe. But how did it sort of make its way into architecture, where it became a desired material? And it sort of goes hand in hand because it's not simply the properties of the materials, the economics, and it's the, how do I put it? It's the technology works hand in hand. Just to give you a very quick sort of synopsis of what I mean by that. New York became New York, not because of steel, not because of coal. It became New York because of its presence in the harbor as an island, Manhattan itself. Number of initial buildings, which were sort of wood frame buildings, which is what more than 70% of New York is covered with, are small buildings. They're not very tall buildings. 25 by 100 foot lot dimensions. They didn't come about through a miracle. They came about because there was a need. We wanted to build housing. What were the materials available? Wood. The maximum span that wood could handle was 20 feet or 22 feet. The longest sections that were available were 22 feet, 23 feet, 24 feet if you pushed it. That determined the typology of the townhouse. The continuous city fabric that everyone admires in New York City is actually a result of that phenomenon. Wood used to come down Hudson River. Shipping became a major deal. So all I'm trying to say is that technology and economics go hand in hand. It's not the quality or the property of the material that sort of changes the scenario. I want to go back to this particular slide. You know that on the left-hand side, all the cons about steel. We talked about it this morning during the panel conversation. The design challenges is what I want to focus on. The history, how it sort of intertwines with the future of how architecture sort of takes off or doesn't take off. Major challenges, as many of the people, my sort of presentation was supposed to be prior to other people who talked about fire code, fire safety, the gauge and the grade of steel. A lot of that material is available to you. There's no point in me boring you with all that information, but it's very critical information. Currently, one of the sort of dilemma that every architect or a designer or an engineer faces, and you know this better than I do, is trying to convince the client why they should use steel. Second part is, if you use steel, number of questions that came up, how are you doing the fireproofing, what is your slab decking, and how do you actually, is it spray-on fireproofing, is it this, is that? Those questions are extremely important. Technology for which does exist. Is it readily available, cheaply available in India, in the places where you want to put up this building? These are the questions that need to be answered. I mean, all of you know about 9/11 and World Trade Center, which are 110-story buildings that came down. But do you also know that there were roughly about 15,000 people in those buildings? Majority of them made it to the ground. The ones who didn't were the ones above where the planes hit. What does that tell you? I mean, people talk about heroes of 9/11, this and that. The two buildings were the heroes, actually, of 9/11. Where they stood there. First plane was hit, 9:15. Second one was 9:01. They stood there for roughly 2 hours, allowing majority of people to get out. Now, that doesn't sound like a design problem, does it? But it's a huge problem when it comes to using steel and appropriate technology applied to the material would yield the type of buildings you want to build. It's not just being euphoric about what you like, what you see in magazines and on the internet. There's also hugely available knowledge base. Again, the same story. Now I'm going to go into what fascinates me about the historical aspect of steel and its advent in architecture. 1851, plate glass became a big deal. Cast iron was available. Huge need. Trade fair. Expo hall, very large. The Crystal Palace. It's called Crystal Palace because they were showing off the new material, glass, the plate glass. Frame is all cast iron. Building is not there any longer. The beauty of this project is, even when it's trying to showcase glass, the use of cast iron is very prevalent. 1930s, again, the major quality of steel. Works fantastic with suspension, tension, less so with compression. Brooklyn Bridge, 1930s, major engineering feat. But again, before actually designing the building, you're actually working on what is it going to take for it to last? How many years are we designing it for? Is it for 50 years, 60 years, 100 years? It's 150 years now. I'm going to switch gears now a little bit. What was architects' role? A lot of infrastructure projects, a lot of special projects were being done using steel. Architects had a different dilemma at that point in time. Housing, houses, certain types of buildings that were being built. Every architect, even many sitting in this room, we all want to liberate the plan. We don't want to be stuck in a box like Ratan was talking about this morning. How do you break the box? Frank Lloyd Wright, the left side building, I mean the photograph, shows you that brick wall. That's the corner that bugged him tremendously. How do I get rid of it? He manages it. He opens up the corner. He liberates the views. He liberates the plan. Corbusier. Believe it or not, the left side diagram, known as Domino House, was drawn up in 1914. It's more than 100 years today. And that's exactly every third building, every second building you walk by uses that principle. Flat slab, columns, and circulation. Domino House, he applies it to architecture. He liberates the ground because the age-old conception that the foundation had to be sort of firmly put on the ground. He removes what we in India call plinth. There is no plinth. The building is floating above. Then comes Mies van der Rohe, who designed many of the brick houses, etc. He looks at steel, understands the properties of steel. He completely liberates the plan. Walls can go any which way they want. They become non-structural because structure is being taken care of by steel. The man who coined the term God is in the detail made us understand that we saw a couple of slides excuse me, of steel joinery between I-beam. The master of I-beam, he actually taught us that structure-wise, steel can be used not in a traditional sense. The column and the plate on top is one way of doing it. Column on the side, plate on the side is another way of doing it. And that changes the sort of way in which you look at architecture and its application. From these humble sort of little projects, this is where he takes us. Seagram Building, the Lakeshore Apartments, 1951. Seagram Building on the right-hand side, 1957. He liberates the plan completely. He gives you an open plan. what is remarkable about Seagram building and unlike Lakeshore, is he gives you an open plan, there are no walls. You put your walls the way you like. It's still hybrid structure because you still have the issue of fireproofing and fire safety. One more thing he does, he introduces what we comfortably use the term curtain wall. And he actually shows you why it's called curtain wall. It does not come down to the ground. It hangs off of the building. It is actually non-structural as far as the building is concerned, but it is structural for itself. And that changed the whole phenomenon, started the whole boom of office buildings because you recognize right away fast execution, precision, absolute detailing that's readily available, tight places like New York City, Chicago, St. Louis. You didn't have to sort of have 100 people working on site. Shops fabricated, brought on site, assembled on site, pretty much. That changed the entire dynamics. So it's a significant project to keep in mind because if you go to Chicago or any other place, basically one of my teachers used to say that when it comes to a house, you can't beat Frank Lloyd Wright. He's done everything that you could think of. Open the corner, break the corner, cave the corner, concave the corner. He's done everything. Or if you really want to push your luck, you can go up to Corbusier, where he actually has a free-flowing walls approach. But when it comes to the iconic curtain wall, an iconic commercial office building, Mies is your guru. All you're doing is you're applying it and reapplying it in a variety of different ways. And it's true, it's very true. And it's not something to be ashamed of because that's what we're doing now. We're bending the curtain wall, we're reshaping the curtain wall, we're going into what I call funicular architecture. And that's important as well. So that's the history I'm interested in, not the linear part, which is important, but you can look it up. This is the history which architects learn from. This is another remarkable building, very important building. A lot of people walk right past it, do not recognize the significance of this building. It wasn't built in 30s, it wasn't built in 50s. It was built in 1970s. It belonged to, this actually, if you go to World Trade Center, the new site, it's right across. In fact, this was the makeshift, morgue during that time, the lower floors. This building is significant. It was put up by US Steel Corporation. They made steel sections, one of the first fabricators of the makers, manufacturers of steel sections. And they went to the city and said, we're going to use steel for the entire building, all columns, and we're going to keep it exposed. Here comes your code issues, fireproofing, this, that, and that. First time it was allowed, only time it was allowed. This building actually has all steel sections completely exposed. Only requirement they made was the intumescent paint was invented around that time to be able to do this building. This is what I mean. You see, I'm a designer, I'm an architect. I get excited about talking about design. But when it comes to India, or any other place for that matter, extremely important. Necessity is the mother of innovation. Boredom is the mother of design. And I'm not taking anything away from designers. All I'm trying to say is it's a luxury. And very often we can't afford it. So being innovative is way much more important. Design thinking drives innovation, which is why this morning when we're talking about slums and Dharavi and all that, I will show one slide and you'll see it. It's a place where you can go and learn about steel, believe it or not. This is your linear history. I can share this image with you and you can look it up online. It's a fantastic infographics that tells you exactly how steel became what it did and what, which were the sort of benchmarks of its development. The last slide is important. I'm going to quickly, critically talk about it. It has a 35-meter cantilever. And to make that cantilever, that you see the corners coming out, is by one of a big name architects, and I have lots of respect for him, Ren Kulas, 35-meter cantilever. And I happen to run into him at Columbia University where I teach occasionally, and I asked him that question. 35 meters cantilever. For what purpose? I love your architecture, but for what purpose? point is this. We figured out this amount of steel that was used to achieve the 35-meter cantilever was equivalent of the amount of steel used in one single building at World Trade Center. We're coming home now. This is where my focus is. Technology is a tool, it's not a means. Culture, context, and climate, do not forget. Whether you are a structural engineer, architect, or plain designer, that's what it is about. Breaking the sun into shadows. Very harsh sun. Sunlight is very harsh, even if it is not directly hitting your buildings. How do you break the sun into shadows? What do you achieve by doing that? You achieve great architecture. Lower 4 slides that you're looking at in this slide, they're contemporary examples. Building by Doshi in Bangalore. The middle one is Corbusier. The third one, the first one is one of the buildings that we worked on. Top is all examples of traditional Indian architecture. I didn't want to make this presentation about me and my work. I'm going to quickly show you as an example of how difficult it is even to achieve simplest goal. You can look up my work wherever you want to, but this presentation is more about putting things in context, putting steel in context. Very simple project, 15,000 square feet on top of an existing building, office space, commercial space, large 35 feet by 45 feet atrium, which on 11th, 12th floor was vacant, empty, open to elements. I don't think I have much time, so I'm going to try and move this very quickly. We basically use steel extensively to work this. Number of skylights, we actually, a lot of your structural engineers will fall off their chairs. We actually cut open the PT slabs to make the skylights. This is in India, which is why I'm showing it to you. The pictures are distorted because somehow this display is not working for you. Thing that you have to understand is lightweight, completely lightweight, steel structure, and flooring is glass to make it lighter. And space is more like a gallery space to be used for local exhibitions and launches. Again, breaking the sun into shadows, even when you want to bring natural light in, you constantly have to work around the sun, because sun works around you, so you better start following it. This is what it looks like from bottom up. This is the building that I was talking about this morning that we were asked to design, and entire structure was supposed to be steel. And we kind of debated with the architects, and we are doing a kind of hybrid structure because it's a residential building. It's not very tall, and the entire skeleton that you're looking outside is actually structural. It's not non-structural. So we moved the structure out and reduced the amount of structure that would be on the indoors just to achieve similar goals. But I'll show you some other examples also. 100% steel structure. You also have to understand, in a place where I work, by code we are required to use steel because of seismic zone requirements. We are floating. 5 of New York's islands are floating. There's high water table, etc. This is a very interesting structure. It's completely exposed structure. Code allows you to expose the structure as long as it stays below 26 feet. Very important fact to remember. Anytime it goes any higher than that, code doesn't allow you. This is another sort of example I'm showing you. It's a hugely popular recreational center, multi-service center. The reason I'm showing it is the sort of malleable qualities of steel. Sometimes you need them. So it's not just the I-beams and and the box columns and whatever have you. It's how you wrap steel around you. This is another example I want to show you so that you get, again, similar example where you have not more than 26 feet height. Every single member is exposed. Intumescent paint is used. It has fire rating that it requires. It's a community center. It's a recreational club. It's a basketball court. And again, I have this modernist streak in me. So I don't like hiding things. I want you to see the structure. Sometimes it's not possible when you go for multi-story buildings, it's not possible. But here every bracket, every piece of steel that's been used is exposed. This is I'm very sorry, these images are terrible because somehow it's squeezed. This building actually is going to be manufactured in India. There's a fabricator who is very enthusiastic about doing these buildings. And so I just told him that, listen, it's fine. If you can work out your cost, etc., we'll design one building for you. And if it really works for you, you can actually replicate it. Entire steel structure, except for the floor slab and the roof slab, which we insisted on making it concrete. I mean, it is steel, but it's basically not exactly the decking principle. We are letting him do insulated slab, and it's 4 inches to 6 inches in different parts. This is the building which is completely sort of, again, we're using metal as cladding, but it's actually structural. It's not non-structural. The building that you see on the right-hand side is also going to use, because it's much taller. It's actually going to go even taller. We designed it for 45 story. It's actually going to go up to 68 stories. That's in Bombay. I'm just going to leave you with this. It's about, majority of people sitting in here are structural engineers. It's about, I don't know exactly how to put it. My grandmother used to say this beautiful, beautiful saying, and I'll never forget that. And she'd say, you cannot pluck, I'm going to translate it, because it's in Sanskrit actually. She'd say, you cannot pluck a flower without disturbing a star. And that's how the sort of global connectivity is all about. Architecturally, structure-wise, you guys talk about the same thing. It's connected, which is where design happens. Everything else is easy, it's manufactured. But how you put two beams together, this is how we design. This actually is a steel structure, much taller. It's about 75 stories tall. And we're working on it. This is how we sort of work on it. I'm going to leave with this slide. Actually, 2 slides. This is India. We talked about material and materiality and sustainability and all that. Wood was one of the first few materials after mud. And after living in the cave and making a mud house, man found wood. And which is why a lot of cave temples which you look at, they remind you of wood carvings and whatnot, which became stone carving, but the original carving was in wood. The beauty of this is it architecture, is it sculpture? I borrowed this slide from a very well-known architect who I have tremendous respect for, Doshi. And the beauty of this is, the positive, negative, what you take away becomes the positive actually, because that's where you live. What you leave in there becomes structure. And the moment you start looking at architecture in that manner, any material that you apply to begins to make sense. So when you translate this back to wood and wood back to steel, which is what happened in the US, initial buildings were wood frame buildings, and we started using steel as if it were wood. And then we changed that. We understood that, oh my God, steel can do a lot more, lot more. It doesn't have to be steel. I mean, Casa and buildings that you see in Soho, they use arches. Goodness gracious, where is the arch coming from? Because steel can be straight. But we use arches because we were so used to using stone and brick. The word architecture, contrary to what most people understand, actually comes from the word arch. The art of making an arch makes you an architect. We followed it to the T. We made steel buildings as if they were stone buildings. This is the slide I'm going to end with. It's a photograph, series of photographs in Dharavi. The beauty, and there was a question this morning about technology and appropriateness in the context. What is the best application? Which is the best? What would be your dream project to use steel? I would say any project where you can achieve the goal. Form follows function. Not always, but majority of the time, because that's what the client wants. If you can achieve the desired goals of the project, any project is as good as any other project for using steel, as long as you know how to use it. And that's basically fundamentally, these guys are using any material that's available to them. Steel sheets, cement sheets, leftover infrastructure, What are they doing? What is beautiful about what you're looking at? I'm not romanticizing. I don't want people to live like this. Not at all. Don't get me wrong. But what am I learning? They are breaking the sun into shadows. They are looking at the environment and responding to it. And architecture comes forward. Thank you, guys.